All right, so we left off here. We were looking at this vector field, and we concluded that this vector field negative 2y what did we say about this vector field? It was special. We found that both these circulation line integrals, remember circulation line integral was a line integral over a closed loop. It starts and ends at the same spot. We found both of these values in this particular vector field were 0. And we said why was that, what was special about this field?
It's conservative though?
Yeah, so we said this was a conservative vector field. And we said that conservative vector fields were what? What made it conservative? So what was it about the field?
It's a gradient field?
Yep, gradient field. Excuse me, sorry about that. And so we found that, and what we said was in a gradient field or a conservative vector field, that any circulation line integral, any and every circulation line integral in a conservative vector field or gradient field equals 0. So that's true for every closed loop C in F. If F is conservative or a gradient field. So that's kind of where we left off last time. So in this field, this negative 2y, which I'm showing, I can make a crazy kind of loop over here. Like Bart Simpson's hair. And going around that closed path C, you'll get a circulation value of 0. The line integral equal to 0, and that will be true for any path you could pick. In a non-conservative vector field, you can have closed loops that are positive value, circulation that's negative, 0. But in a conservative vector field, every closed loop, no matter which one you pick, will give you a 0 value of the line integral. Okay, so let's take that a step further here. Let's look at so here is a path through the same vector field. And I'm going to call that C1. And it goes from 3, 0, call that point A, to 0, 3, call that point B. And so the line integral over C1 through F here. Let's do this. I'm going to write it that way. Okay, so there's our conservative vector field. So the value of this line integral from A to B along this path C1, since we're in a conservative vector field, is 0. Is that right?
Not necessarily. No.
I thought all the line integrals were 0 in a conservative vector field.
It's not a closed path.
Yeah, not a closed loop, right? It's got to be a circulation. We gotta go all the way back to where we started. All right, so this is not necessarily true. Probably is not true. Oh, and this reminds me, I forgot to announce. The quiz from Friday, which I said you'd have extra time for, is due tonight at midnight. So if you've still forgotten to do Friday's quiz, you have till tonight at midnight. I want to make sure that everyone remembers this one. So don't forget Friday's quiz, due tonight at midnight. All right, so let's predict this. Let's look at the vectors and predict what this line integral over C1 would be, positive, negative, or 0.
Positive.
Yeah, so if you take if you take components of the vectors along the path parallel to the path, they will point in the direction of the path, right? And so we're going to accumulate along that path, and the vectors are pointing, you have components of the vectors pointing in the direction of the path, therefore positive. And we've done those kinds of exercises before. All right, so now I'm going to pick a new path, and it's going to be from B back to A. I'm going to call that C2. From B back to A. And so we concluded that this line integral over C1 was positive. Is that right? So I'm going to tell you, without calculating it, I'm going to tell you that its value is 10.5. Or about. Okay? So we know how to do it. We'd parameterize the path. We'd rewrite our vector field in terms of x and y from the path. We'd find our dr, do the dot product, do the calc 1 integral. So I'm telling you that value is 10.5. Now I'm going to do the line integral C2 in the same vector field, which starts at B and takes the straight line segment back to A. And we want to find that value. Okay, I'm done. Anybody else got it yet?
Would it be negative 10.5?
Yeah.
Okay, a couple people are saying negative 10.5. Why would that be negative 10.5?
Because any closed loop in the conservative field has 0.
Right. C2 then closes the loop of C1. And since it closes the loop of C1, then going around that loop has to be 0, and so C2 would have to have the equal and opposite value to C1 in order for that closed loop to have a line integral of 0, a circulation value of 0. So does it make sense that heading back from B to A has to give negative 10.5? Should make sense. And that's just an extension of the fact that every closed loop in this conservative vector field will have a circulation value of 0. Oops. I don't want to do that. What did I do? Okay. That's enough. All right, so now I got a new one, C3. C3 goes from B to A along 2 line segments. C3 is this one. It starts at B, it goes horizontally to here, and then vertically down to A. So it's a piecewise line integral that goes to this point and then down. What about the value of that?
Negative 10.5.
Negative 10.5. Does it make sense? Yeah, because it's another closed loop, right? So A to B, B back to A makes another closed loop. All right, what if I start here at B? And I kind of go wavy like this. And I go straight down like this. And then I make a circle like this. And then like that. So here is C4. What about the value that starts at B and takes this crazy piecewise path back to A? What about that?
Should it still be negative 10.5?
Negative 10.5. Because that's another closed loop. From A to B and then along C4 back to A is a closed loop. Has to be 0. Every single circulation in this vector field has to be 0. So the only way that could make a 0 circulation is if along that path from B to A is negative 10.5.
How can we verify?
You broke up there. I couldn't understand your question.
How can we verify that is the conservation vector field is 0?
Because we said this was a conservative field. And in a conservative gradient field, every closed loop has a circulation value of 0. So how did we so I'm not sure what your question is. How do we verify that this was conservative?
Yes.
So we did that. Okay, so I should have mentioned that. We did that last time by looking for a potential function. So remember last time we said, is there a potential function, a multivariable function, whose gradient is this vector field? Can we write a function if you took the gradient of it, you'd get this vector field? If you can, then it's a gradient field. And we found that it was negative 2x plus y squared over 2 plus c. And this c being a constant, not the c standing for the paths. Does that answer it?
Yes.
Okay, but I'm glad you asked that because, well, let's go back to this what we're talking about here. So what do we notice about then any path from B to A? What's true about any path from B to A?
It's equal to negative 10.5.
It's got to be equal to negative 10.5. No matter how I go from B to A, it's going to complete a closed loop for which the first part was positive 10.5. So every path from B to A has to give us a line integral of negative 10.5. And what could we also say for about every path from A to B?
Has to be positive.
Yeah, every path from A to B would have to be the opposite of every path from B to A. So every path from A to B would have to be positive 10.5, just like this circle was. Because if you go the opposite direction in a line integral, you're going to get exactly the opposite value. So what we have here is what's called in a conservative vector field. So we have conservative vector field is a gradient field. Every closed loop is equal to 0. But now we have another conclusion to that, and that's what's called path independence. Okay, so given any starting point, any ending point, every line integral from that start to that end is going to have the same value. The value of the line integral will be independent of the path that you take. All that matters is the start and the end. So the value of depends only on the start and end point, not the path. So given a fixed starting point and a fixed ending point, every line integral from that starting point to that ending point will have the same value. And we just showed that that's just a direct result. You can argue that pretty easily from, like we just did, from the fact that every closed loop has to be 0. Okay, any questions on that? All right, there's something else. So in terms of how do we know this was a gradient field? So far, to find out if something's a vector field's a gradient field or not, what have we done? We start working on it like it is, trying to find the potential function. And if there's a potential function whose gradient is our field, we've said it's a gradient field. And if it's impossible to find the potential function, we said no, it's not a gradient field. So that should be familiar. Okay, but there's something else. Do you remember what? So if this is a gradient field, what is negative 2 and y? So if you have a gradient field,
The partial derivatives.
yeah, they're partial derivatives. Remember, that's what gradient is. It's the partial derivatives. So that we know is the partial with respect to x. and that's the partial with respect to y. What was the relationship we had with second partial derivatives? Does anybody remember? We had a relationship with second partial derivatives.
Were they equal to each other?
Well, there's four. There's four second partial derivatives. So
Was it like inflection points when?
it's not necessarily so.
Because x, y, and yx were equal, but
Yeah.
xx and yy were different.
Yeah,
right?
yeah, definitely, right? Yeah. So the relationship we saw was that fxy equals fyx. This was called Chloro's theorem. We didn't spend a lot of time on it, but we did mention it, and you had some you saw that in your homework. That if you took the second partial of the first partial of x with respect to y, and then you took the second partial of the first partial y with respect to x, you get the same function. Those are equal. So this is a way we can use this to verify if we have a gradient field or not without trying to find the potential function. We can come here and we can say, okay, if -2 was fx, then what would fxy be? And if y was fy, what would fyx be? So what is this? So we got the partial with respect to x. What's its partial with respect to y? What's that?
0.
Zero. And here's the partial with respect to y. What's its partial with respect to x?
0.
0 again. What do you notice? Those are equal. So by Chloro's theorem, we truly have, these truly are partial derivatives. And this is a gradient field.
I'm a bit confused about how we drew that conclusion.
Chloro's theorem says, so we start with this premise. Do you understand that? We saw that a month or so ago, a couple weeks ago.
Mhm.
So if this is a gradient field, then this is the partial with respect to x, and this is the partial with respect to y. So if you find the mixed second partials and they're equal, then you're saying, oh, this indeed was the partial with respect to x and the partial with respect to y. So if Chloro's theorem holds, you can conclude that those are valid first partial derivatives.
So if dx and dy, if that was not a gradient field,
These would not be equal.
okay. And why is that?
We didn't get into the the proof of that. We never got into the proof of that.
All right, thank you.
Yeah, that would take some time. Okay, so here's another conclusion about conservative vector fields or gradient fields that, if then what? Py would equal qx. So this is already this would be the partial with respect to x. So if you take its partial with respect to y, it would equal this one, which is the partial with respect to y, its partial with respect to x. In other words, fxy equals fyx.
Quick question, Professor.
Sure.
For the conservative field and the gradient field, are those terms used interchangeably?
Yeah, pretty much. I mean,
Awesome.
they mean different things, but they're equivalent statements. So this conservative vector field is like, it's implying the idea of every closed loop is 0. You have conservation of energy around every closed loop. Okay?
Awesome. Thank
This is then focusing on the fact that the field is a gradient of some potential function. But if one of those is true, then the other is true.
I'm just wondering, is there other types of conservative vector fields, or is that just...
I'm not sure what you mean. That are not gradient fields?
Yeah.
No, this is the point. The point is,
Okay, that's what I was wondering.
Yeah.
Okay.
these arrows go both ways. All these arrows go
Okay.
both ways, not just the one
Okay.
way. If it's a gradient field, it's conservative. If it's a conservative vector field, it's the gradient of some potential function. Okay, so we're seeing all these results and consequences of having a gradient field. And so we're starting to make a list of all these consequences and results. All right. Any questions? Okay, so let's take a look at this one then. So here is the same vector field. This is, oh, I think did we have slightly different? Was that one negative 2y? Yeah, that was negative 2y. So here's 1y. That's also a gradient field. And so here's a path along the unit circle. Let's look at these 3 paths. And we're in F2 here, 1y. And we're going from we'll go this way now. Go from point A to point B. And so we're going this way. And what can you say? So let's predict here. Is from point A to point B, is that line integral going to be positive, negative, or close to 0? What do you think?
Close to 0?
To 0.
It will be close to 0, but I think we can conclude whether it's either positive or negative.
Positive, because it's going
Yeah.
towards the positive direction.
If you look at these vectors at the beginning, to look at their components in the direction of the path, it's going along with it, right? Now here it's very 0-ish, right? It's like very 0-ish. But this first part gives us a positive result for that. All right, what about this one, C3? Positive or negative?
Positive.
Yeah, so we got a little bit negative here at the beginning. If we look at these components, a little bit negative. Now this is 0-ish through here, but then definitely all these components here of these vectors along the direction of the path are positive. So a little bit, seeing it negative, 0-ish, then certainly positive. What about the line integral along C1 versus C3? We said they're both positive. Are they equal?
Yes.
We have 1 for yes.
Yes.
2 for yes. How do you know for sure, right? I mean, if we're just eyeballing, how do you know for sure that those are the same positive value?
It's a closed loop.
Same start
In
and
a
end
gradient
points.
field.
Yeah, same endpoints.
Same endpoints, and we're in a gradient field, right? So that's definitely a conservative vector field. Same start and endpoints means every path from A to B is going to give us the same line integral. So C2 as well. They're all equal.
Exam, and then our final exam.
Jacob, hey Jacob, your microphone's. Hey Jake, thank you. All right, so every path from A to B, C1, C2, C3, any weird one you want to draw, they're all going to give the same line integral because this is exercising path independence, right, in a gradient field or a conservative vector field. Okay, so now let's look at a different vector field. And this one. So now negative. Sorry. There we go. Okay, negative x, x. So I want to know just quickly, just find out really fast if this is a gradient field or not. What can I do? I want to know partial derivatives, right? So we're asking, is negative x a partial with respect to x? Is positive x a partial with respect to y for some function f? How can we check it?
Take the first one with respect to y and the second one with respect to x.
Yep. First one with respect to y. Take the second one with respect to x. What do I get for the first one? So this negative x With respect to y, partial
Yeah.
derivative is? 0. Take the partial derivative of this one with respect to x, and you get
1.
1. Conclusion,
Not a conservative field.
not conservative. Chloro's theorem does not hold. Not a gradient field. And let's confirm that by sight, looking from A to B here. So what about the line integral across C1? Positive, negative, or 0?
Negative.
Yeah, and like kind of zero, like low negative here, but strongly negative through the whole second half of that path. So this is F1 now. Or I could do just write negative x dot dr. Certainly negative. What about C3 from A to B? Positive, negative, or 0?
Negative.
Negative, right? It's still going against the direction of the vectors in the field the whole way. But can we, from sight, conclude that these are the same or different?
No.
So look at these vectors. Look at their magnitudes, right?
C3 looks a little less negative, but the arrows are small.
Yeah, and now look at the magnitude of the vectors that we're going through on C3. So these are clearly lower magnitude vectors, and it'd be very close to look like they're really small here. But yeah, you have much bigger negatively directed vectors in path 1 than you do in 3. So we'd expect a bigger negative for C1 than C3, and this is underscoring that we don't have path independence. It's not a conservative field. So we could write that the the line integral for C1 is less than the line integral for C3, just by observation. But we know they're both negative, both less than 0. So we don't have path independence. So we know we can get a negative line integral from A to B, and we can get varying magnitude of negative. But we can also get line integrals from A to B that are 0 and positive also. So let's do that. If we zoom out here. Oh, we can just erase everything. So if I zoom out, okay, we know we can find negative. In any of these paths through the first quadrant, we can create a negative line integral from A to B. What about positive? Can you see a way to get from A to B that results in a positive line integral?
Could you go like leftwards and loop around to B?
So go straight left?
Almost like completing a circle, but going left.
Yeah, so let's see
If we
here.
go down,
So instead of a circle, I'm going to kind of make a squarish kind of path. How about that? So if I go from 0, 1 to negative 1, 0, what would be that line integral right there?
0.
0. And then if I went from negative 1, 0 to 0, negative 1,
Positive.
positive. And then if I went straight to B from there, maybe?
0.
That segment is 0.
That segment is 0. So here's a path. Call it C4. What would the line integral of C4 be?
Positive.
Positive. See that? So taking this path, I can make that line integral from A to B be positive. Okay? Is there another positive path that's something a lot different than that?
Can we go straight down? Is that equal to 0?
Yeah, this is on the y-axis, x equals 0, so all the vectors here are 0. Yep, so all the vectors along the y-axis are 0 because the vector field is negative x, x. So if you went straight down, then what would you want to do from there?
I'm not entirely sure.
Well, maybe if we went straight down, way down here, past -1, and then we went orthogonally to here, and then we went like this. Then this would all be 0 because the vectors are all 0. And then this would all be 0 because we're going orthogonal to the vectors. And then this last little part would make it positive. So that path would have a positive value of the line integral. Okay, what about 0? So can we make a path that results in 0 value of the line integral from a to b? So we've seen negative. We've seen a couple examples of positive. What about 0?
Would we go straight down from A, and then instead of going a little bit past B like we did last time, we make a line between a point on the y-axis and B so that it's orthogonal to the gradient field?
I think that's what you mean, like that?
Yes.
Yeah, so 0 vectors all along the y-axis, and then orthogonal the rest of the way home. 0. That'd be a line integral of 0. Anybody see another way? That's much different than that.
Using the axis of y and axis of x is on the path of the y and x axis.
Okay, I didn't catch it. Can you try one more time?
Would it be okay to use the path of the y and x axis?
Oh, like down to here and then over like this?
Yes.
Would that give 0? What would that give? Is that 0?
Would that be kind of a little bit negative?
That'd be negative, right? That'd be negative because this would all be 0 here, but then coming along the x-axis, you have components opposing the direction, right? Okay, so that's another good example of a negative one. What about another example of 0? How about this? And then, how about this? Is that 0?
Yes.
So it's 0 because you're orthogonal to the vectors. Then you have a positive contribution to the origin, and equal an opposite negative contribution to B. So it'd be 0, and then it'd be positive to here, and then you'd be back to 0 when you get to B. Okay, so this is underscoring what happens in a field that's not path independent. It's path dependent. You can find given a starting and ending point, you can sometimes in a path dependent field you could find paths that give us a positive line integral, 0 line integral, or negative line integral, all for the same starting and ending points. So underscoring that path dependence means the path matters for the value of the line integral. Okay, any questions? Okay, so let's kind of apply some of these principles here in a problem. So we're going to Middle Earth and the mountains of Mordor in Middle Earth. And those mountains are modeled by this multivariable function. Slightly complex, okay? Kind of it's a rational function of sine and cosine terms. And so, turn here. So this yellow point here is our heroes are starting there, Sam and Frodo, and they need to get to this turquoise point here. Why is it doing that? There we go. And so Frodo and Sam have a combined mass of 75 kilograms. And they need to get from point A to point B so they can toss the ring into the fiery abyss in Mordor here. And so how are they going to do that? It's a treacherous journey. So something like this. So here they go. And so here they're making their way, and our hero, Sam, says, "I can't carry the ring, Mr. Frodo, but I can carry you." And so they're gonna make this path from point A to point B, so they can toss the ring and save Middle Earth. Okay, so if they have a combined mass of 75 kilograms, and the starting point is negative 0.5, negative 0.5, 0.1, and these are our units are kilometers. So of course Middle Earth is going to be on the metric system, not the imperial system. And then our final point is 0.85, 0.65, 0.98, and they're going to go along this path. We want to figure out how much work does Sam do to get them from the starting point to the ending point. Okay, and so why does it take work? Because they are in a force field, which is a the field gravity. So the path will be according to a path along this multivariable surface, and the field is this field that I'm showing with the black vectors, which is gravity force field. So I'll call that F, and that's a three-dimensional vector field. And what would that be? What is that vector field? That is the vector field of gravity.
0, 0, 0, negative 9.8.
Good, okay. Close though. So this is the force of gravity, not the acceleration of gravity, right? So it's not just going to be negative 9.8, but it's going to be
75 times negative 9.8.
Yeah, so it's going to be negative mg. So whatever the mass is times the acceleration of gravity gives you the force of gravity pulling on that object. Okay, so in our case, for our dear friends, it's going to be negative 75 times, assuming that Middle Earth has the same gravitational pull as our great Earth. Negative 75 times 9.8 is the acceleration of gravity. Okay, and that will be in what? That will be in newtons, and our distances are in kilometers, so our force unit will be kilojoules. Kilojoules. Okay, so now, so we're gonna write, so the work that the field does on they're hobbits, right? Sam and Frodo? Is going to be the line integral over the path C, so this is the path C, of f dot dr. And then the work that Sam does will be the equal and opposite to the work that the field does on them. So, but just to keep it our standard line integral, we'll do the line integral. That's the work the field does, so then the work Sam does is equal and opposite to that. Okay, so what do we got to do? We got to parameterize C. So we're going to have to figure out the vector function, the three-dimensional vector function, that's that path along our multivariable function, which is this, right? So that path is going to come from this function here. So can we do it? We got to find.
But we don't need to.
So R sub C. Well, we say, yeah, exactly. Maybe we can do it, but we sure don't want to. All right, this is going to be awful, right? Terrible, the worst. So, but we need to know how much work the field is going to do on our friends, and likewise how much work our friends have to do to get from point A to point B. So, is there another way besides trying to parameterize this awful curve based on this awful surface of our mountains?
Let's make the path a straight line.
Okay, so
Check if it's like the second partials line up or something, so that it can't be.
so can we do a different path and get the same value for the line integral? Yes or no?
I think yeah, we can just pick any path.
So when can we pick any path? So are we able to pick another path in this instance?
Yeah.
Why?
When the vector field is path independent.
Right. So how do we know if it's path independent or not?
F is conservative.
If we have a conservative vector field. So here's our vector field. 0, 0, and a constant.
Or it can be
Is this a conservative field? So we don't really have, there is a Chloro's, like analogous Chloro's theorem for R3 vector field, but it's complicated and it takes 3 equations, and we don't want to deal with that. So we want to just kind of quickly look at this and say, is there a potential function that has this as its gradient?
Yeah.
Okay. Right, 0, 0, and a constant. That's a pretty easy gradient field. I mean, that's a pretty easy vector field. Just all constant vectors pointing down. So what would the corresponding potential function be? So f, x, y, z. What function would have this as its gradient?
Negative 75 times 9.8 z plus c.
Yeah. And we'll make the constant 0. So it's the constant, we don't need a constant. So yeah, so negative mgz, or negative 75 times 9.8 z. The partial derivative with respect to x is 0. The partial derivative with respect to y is 0. And the partial derivative with respect to z is that. Got it. So therefore, we have a conservative gravity field as a conservative field, and therefore it's path independent. So we can, to get the amount of work along this awful path on that surface, we can instead do the straight line path. It doesn't matter that it's through the air and cuts through the mountain. It doesn't matter because we're in a conservative field. The amount of work on that straight line path will be the same as for any other path. So we'll call that path L for line. So we want to avoid the path C. Instead, we want to do the path L, and I can make that pretty. Although I need to change the color of it. Let's make it, see if it shows up if it's blue. Yeah. Pretty well, not great. Does the bluish purple line show up?
Yeah, we can see it.
Okay, cool. All right, so the path for C, instead we want to do the path for L, which is the line. And so for time's sake, so the way I showed you last time was to do the starting point, and that was our negative 1/2, negative 1/2 0.01. All right, plus t times the one vector that takes you from point A to point B. That way, when you get to the integral, you can go from t equals 0 to 1. So we need the one vector from the start to the finish, which would just be subtracting coordinates here. So that'd be plus t times 1.35 plus t times 1.15, and then 0.01 plus t times, what will it be, 0.99, 0.97. So there's my vector parameterization of the line using the starting point, and my parallel vector is the whole vector from a to b, and that way my t can go from 0 to 1. So now we're ready to do the integral. The integral from 0 to 1 of f, which is 0, 0, negative 75 times 9.8, dot. We're going to go long, sorry. We're going to go about 5 minutes over. And then dot dr, right? Dr would be the derivative of each individual component, dt. So it would be 1.35, 1.15, 0.97 dt, and that from 0 to 1. Okay, and this would be the work that the field does on Sam and Frodo, our hobbits. No, they're not hobbits. Are they hobbits? I forgot.
They are.
They are. Okay, they're all hobbits. All right, okay. All right, and so, thank you. Important to know that for sure. Okay, so then we'll get the integral from 0 to 1 of negative 75 times 9.8 times the 0.97 dt, which will equal negative 712.95 kilojoules. And this is the work that the field is doing on the travelers. Okay? And it's negative because it's against, right? They're actually going up, so they're going against the direction of the vectors. Okay, any questions on that? So I'm doing the line integral by path independence. I'm doing the line integral across the segment rather than this nasty path along the mountains. And we can do that because we have a conservative field and we have path independence. Okay, what's another way to find, do you remember from physics, another way to find the work from going up from a point to another point?
Force times distance.
No. Well, that's what this was. This was integrating all the little force times distances. But you remember,
just take the integral of all of it, so force times the differential with respect to x, or in this case, in terms of multivariable functions.
That's what this is doing. This is doing the force times distance approach and doing it a step at a time. So that's
just straight up.
So if you remember from physics, the work is the difference in potential energy. So it's a potential energy final minus potential energy initial. So the potential energy at the end minus the potential energy at the beginning is the difference in potential energy, and that would be the work required to get from the lower position to the higher position. So, and how do we calculate potential energy? Anybody remember?
It'd be MGH.
MGH final minus MGH initial. And let's do it. So MGH would be negative, in this case, 75, positive now, times 9.8, times height final, which is 0.98, minus 75 times 9.8 times height initial, which is 0.01. And if you do the math on that, you get the same thing. But now this is positive because this is the work that has to be exerted to get up that. So it's equal and opposite to that. So it's the work that Sam does. The work that Sam does is the opposite of this. Okay, but here's the big takeaway. What do you notice about the potential energy formula? Anyone notice?
It's only dependent on height.
Okay, it's true. That's true.
Is it basically our potential function?
Look. Isn't it the exact same thing as the potential function? It is. It's the same thing as the potential function, and that's why it's called a potential function, because in the context of gravity and work, the potential function is like the potential energy at that height. So this integral that we calculated, this line integral, f dot dr over the path L, is the same as, so that's the work. So it's actually the opposite of this. But that's the work computed step by step. F times force times distance, all the way up is equal to the difference in potential energy. Well, that's the same as the difference in our potential function. So it's going to be F evaluated final minus F at the initial point. Because this potential function is truly the potential energy at each point. So we get another way of calculating the line integral in a conservative vector field is find the potential function, evaluate it at the final point, evaluate it at the initial point, and subtract. And that should, to calculus experts, that should seem very familiar. What is that?
Fundamental theorem of calculus.
Yeah, so this is the fundamental theorem of calculus, but now for line integrals. F is like the derivative of f, right? It's the gradient field. The gradient field is the derivatives of our potential function. So this is like antiderivative, right? It's like the antiderivative evaluated at the endpoint minus the antiderivative evaluated at the starting point. Gives us the same as integrating step by step, bit by bit, using the rate function, which is our gradient field. Okay, sorry I kept you long. And so we didn't, obviously don't have time for a quiz and actually didn't make it quite far enough for the quiz. So the quiz is, Friday's quiz is open till midnight tonight if you haven't taken it yet. And Wednesday's quiz will incorporate stuff from today and Wednesday, okay? So I will stick around for questions as always. Otherwise, you got homework due Wednesday night, web work. Make sure you're working on that. You should be able to do most of it now. And then if I don't hear from you, I'll see you on Wednesday. Have a good day, everybody.
Thank you, Professor.
Sorry to keep you late.
Professor, I understand that how this force field is a conservative field, but can we call it a vector field or not a vector field? I mean a gradient field because it's in 3D. I thought gradient fields have to only be in 2 dimensions.
Oh no, you can have gradient fields in any dimensions.
Oh, okay.
Yeah, no. So we everything we've done so far was in R2 when we're talking about it, but no, this is definitely, gradient fields can be in any dimensions.
I guess because mostly we work in R3, so the gradient becomes R2, but so
Oh right.
So if this 3D vector or vector field with 3 dimensions was a gradient field, then the potential function would have be in R4.
Yep, that's right there. See that? So that's W is a function of X, Y, and Z.
Okay. Yeah.
Yeah.
All right.
You're right.
Makes sense.
Exactly.
Thank you.
Yeah, sure.
Professor?
Yeah.
When is the final exam?
Thursday night. I talked all about that at the beginning of class. Thursday night, December 3rd.
Okay.
7 p.m.
Okay, thanks.
Okay.
So, professor, in these questions, the mountain one, like the potential energy initial will be the same function for the gradient force.
No, it's the same as the potential function for the gradient field. So here's the gradient field. The potential function of this is the negative mgz. Remember that? We did that?
Yes, because we only have the z direction on the gradient.
So the partial with respect to x is 0. There it is. Partial with respect to y is 0. There it is. Partial with respect to z is mg, or negative mg. So then,
mass times acceleration. Negative mass times acceleration.
Yeah, force. It's force.
Okay.
This is because it's a force field, and so these are forces. So this is the force.
Thank you so much.
Okay, sure.
So, Professor Zahanlo, I'm just confused. Why is it it's a negative mass rather than the positive? Because are we taking the direction of the z into opposite of the vector field?
Well, so what's happening here is the reason we got some negative sign stuff going on. It's because there's the work that the field does on Sam and Frodo, and that's equal and opposite to the work that Sam and Frodo do to get up. So if you truly do the line integral of this vector field, you're going to get negative because they're going in the direction opposite of the direction of the vectors. And so that means that the work that they do, or the work that Sam does, is positive. So here I'm calculating the work of the vector field. But then when I did potential energy final minus potential energy initial, that's for Sam. So that's why it's positive.